Hey YouTube, today we're going to be going over another powerful tool in our toolbox for large language models, GPTQ-for-bit quantization. We're going to be going over the mathematics of how it works, and finally how to use it with GPTQ-for-LLaMa. Now if you'd like to skip the mathematics, you can skip ahead to the chapter on using GPTQ-for-LLaMa, but if you'd like to stay for the mathematics, we'll be going over emergent features, what is quantization, the differential geometry behind it, and finally how to implement 4-bit quantization. So let's get started. So before we get into 4-bit quantization, let's review a few concepts. So let's start with what neural networks are and why quantization is important to them. So neural networks are made up of neurons and weights that connect those neurons, and these weights can be represented in a matrix where weight 1 through weight nm can be represented in that matrix. So if we look at the input in the hidden layer for this example, we see that we have a 3x3 fully connected network. And that network can be represented by a 3x3 matrix, and let's say the values in that matrix are these weights. So what we would like to do is to change these weights from 32-bit floating points to 8 or 4-bit integers, making the network 4 or 8 times smaller. And so how we can do that is through a process called quantization, where 0-point quantization is probably the most common, while there are other techniques. So how we do this with 8-bit is we would like to combine the weights in this matrix between -127 and +127. And how we do this is we first find the highest value in our weight matrix, which in this case is 9.17. So we take this 9.17 and divide 127 by it, and we end up with about 13.84, and we call this our scaling factor. So we take the scaling factor and multiply every value in the matrix by it, and then round to the nearest integer. So for example, if we take 0.84, we would multiply this times our scaling factor of 13.84, and we get roughly 11.6, which rounds to 12. So now let's move on to the next concept. So the next thing we need to know is a concept from calculus called the derivative. Now, if you haven't had calculus, the only thing that's important to understand here is that this is measuring the rate of change of something. How quickly is it changing? And in this case, if we have some function that describes our position, we can know our velocity because that's the rate of change of position, and we can know our acceleration because that's the rate of change of our velocity. And how we typically notate this is with this dy dx form, or f prime of x, where the dash means prime. And this is called our first derivative. But we can also have second derivatives. So if we go back to our position function, we can skip velocity and go straight to acceleration. And this is notated as this 2 superscript and subscript notation, or f double prime of x. Now, these derivatives are with respect to single variables, but we can also have partial derivatives, which let us look at multivariable functions. So if we have some f of x, of y, and z, then we can take a derivative with respect to one of the variables while holding the others fixed. So we can look at how only that variable is changing without updating the others. And why this is important is this plays into the Hessian, which is used to help update our weights for 4-bit quantization. And really the most important concept here is that it allows us to look at how the loss is updating. So what is the error in our network as we're updating our weights? And that allows us to minimize that loss. And we'll see how this plays into 4-bit quant once we get there, but now we can talk about emergent features. So the last thing we need to know before 4-bit quantization is emergent features. And this is a phenomena of large neural networks where various layers are agreeing on how to label certain features from the input. And this can be thought of as how the network embeds knowledge within itself. And so we want to be careful that during the quantization process, we're not accidentally overriding these emergent features. So we need to know how to find them. And they typically present themselves as being weights in a layer that are significantly larger than the rest of the weights in that layer. So for example, if we look at column 3 here, we see that these weights are significantly larger than the rest of the weights. So we would want to leave these as floating point values and handle the rest as quantization. So what happens is we end up with 2 sets of values. We have one matrix where we're going ahead and quantizing the values into integers. But then we have another matrix where we leave them as floating point values, and we leave them as these kind of larger representations. And that allows us to preserve the emergent behavior of the network while also getting the benefit of the quantization. So now we can move on to how do we actually do 4-bit quantization. Our goal with 4-bit quantization is to minimize the loss function, or otherwise the error that we're introducing during this quantization process, and to compute the best possible parameters for this quantization. So to do this, we're going to follow the following pseudocode. We're going to extract the weights for all of our layers and then process them layer by layer. So this is a layer-wise quantization process, so we're not doing all the layers as a batch, rather we're doing them one by one. And then we're going to find the Hessian for each layer. And remember, the Hessian tells us how our loss or error is affected by updating these weights. But the Hessian does have a small problem in that it tends to overfit a network. So we'd like to introduce a small dampening factor to ensure that we're not overfitting the network. And then after doing the dampening factor, we're going to find the inverse Hessian. And why we do that is we want to understand the loss sensitivity for values as we're updating these weights. So higher values are less sensitive and lower values are more sensitive, and you'll see why in just a moment. So now we're going to start processing our weights and quantizing them. And to do that, we're going to pick the first weight in our layer and quantize it using 0-point quantization, just like we saw with 8-bit quantization, but this time with 4-bit. But this is where the inverse Hessian comes into play. So we're going to compute our total error by taking the original weight and subtracting out the quantized version, but then dividing by the relevant value in our inverse Hessian for this particular weight. And like we mentioned before, the higher the value, the less sensitive it is. So the smaller the error, but the smaller the value, the higher the error that we've introduced into the network. So what we'd like to do now is balance out this error that we've introduced by going back through the rest of the unquantized weights and adjusting them by the error that we've introduced. So for example, if we look at weight 1m, we would update it to be this. Weight 1m would equal weight 1m plus this error times its relevant value in the Hessian. And remember, in this case, if it's a larger value, we can adjust this weight more without having to worry about introducing error. And for smaller values, we need to adjust it more, we need to adjust it less. So once we finish this, we will start quantizing the rest of the values and repeating this process until we have quantized all of our values. And the end result of this is generally a more stable network, especially in this kind of mixed model where we're only updating the values that aren't emergent and leaving the emergent values in their floating point representation. Now let's move on to using a llama library to do GPTQ 4-bit quantization on a llama model. Now, if you'd like to be able to do GPTQ 4-bit quantization on llama models, we first have to check out the GPTQ-for-LLaMa repository, and that will be in the description below. So once that's downloaded, we're going to cd into the directory for it, and we're going to install the requirements for it using pip. And that takes just a little bit of time. Now, if you're a Windows user like I am, you'll have to use WSL unless you're willing to build the dependencies manually. I wasn't, so I just used WSL. Now, once we have everything installed, now we can do the 4-bit quantization. So we have to have an unquantized model that we plan to use, and I already have that. So let's go ahead and go through this command and see what it does. So we're going to call llama.py. We're going to tell it where our model is, and we're going to tell it the number of bits. In this case, we plan to do 4-bit quantization. We want to use true-sequential. We want to use act order. We want to use group size 128, and then we're going to tell it where to save it. In my case, output.pt. And this command line will also be in the description, though it's also in the repo. So now we can go ahead and run this command, and this will take a significant amount of time to run. But the 7 billion and 13 billion parameter model should be able to run on a variety of systems, and I'll also try to include the requirements for this in the description as well. Now I'm going to go ahead and let this run, and I'll come back once it's done. So once this is done processing, you should see the following, and I kind of wanted to show y'all what you should see as it is working through quantizing the weights. You're going to see a lot of printouts for these layers as they update, and if you see any really high weight errors, you should probably think that there are some issues going on, but other than that, as long as you use the default settings, this should just run without any pain. It takes about 20 to 25 minutes on my machine. Your results will likely vary, and that's it. If this was helpful for you, please like and subscribe, and let us know in the comments what you'd like to learn about next, and stay tuned for our continued conversation about how large language models work.